Hello everybody, welcome to our first lesson on exponential and logarithmic functions. Today we're going to be going over just exponential functions, specifically looking at graphing exponential functions. By the end of this lesson, we will be able to identify, graph, and transform exponential growth and exponential decay functions. Okay, so let's get right into it. Okay, first things first, what are exponential functions? Well, exponential functions are just functions with an input, or our independent variable, okay, is the exponent, okay? It's in the exponent of some base, okay? Now, important to note, this is the fastest growing of all of our functions that we've seen thus far, okay? Even faster than, say, y is equal to x raised to the 10,000th power. Okay, this is because we're just doing something different than raising something to a power. These exponential functions with the variable or the independent variable in our exponent is going to drastically change how our function behaves. Okay, and it is our fastest growing function that we know, okay, that we can calculate right now. Okay, another thing to notice, it has a horizontal asymptote. It does not have a vertical asymptote. Okay, we're going to see it kind of looks like it does have a vertical asymptote, but it doesn't. Just a horizontal asymptote, which, if you remember, our horizontal asymptotes are all about end behavior. Okay, end behavior is what our, if I spelled that right, is what our horizontal asymptotes show us. Okay, so we do have a horizontal asymptote for our exponential functions, and our exponential functions are one-to-one. One-to-one meaning that they do have an inverse, okay, which we will take a look at in future lessons. But it does have an inverse because it is one-to-one. Okay, our domain is all real numbers, and it kind of looks like it's not all real numbers, but it is all real numbers, which is very important to realize, and a little happy face there because we're always excited when our domain is all real numbers. It makes life nice and easy for us. Okay? And some applications, why we need to know these things. Very important in applications like population growth, bacteria growth, as well as a lot of financial situations where we can look at exponential functions to help us gain money, earn money, become rich people, and stay rich, and all that good stuff, okay? So the general shape that we work with, okay, is going to look something like this. Now this graph is f of x is equal to 2 raised to the x power. Okay, so again, this is what we're seeing here. My independent variable, my input, is my exponent. It's in the exponent of some base, okay? So this is what makes this an exponential function, okay? Because it's in the exponent, so that makes sense, right? Variables in the exponent, now I have an exponential function, okay? So let's take a look at our two types of exponential functions. We've got exponential growth versus exponential decay. Okay, you guys have probably heard these terms before, but as you would guess, exponential growth is when we are growing. Say a population is growing or something is growing exponentially. Okay, so our kind of parent function here is going to be f of x is equal to b raised to the x power. And here b is greater than 1. Okay, b is greater than 1. So our range now we see is f of x is greater than 0. Okay, that's when I have no transformations, which we're going to look at in the next slide. Okay, but if I have no transformations, then my range is just the output f of x is greater than 0. And our general shape, like we saw last time, is going to look something like this. Okay, you can see as I move along my domain, I'm growing, right? Or my output is growing. Okay, that's why we call this exponential growth. Okay, because as I move across my domain from left to right, my output is growing exponentially. Okay, and then for exponential decay, okay, we've got the same sort of setup. F of x is equal to b to the x, but now b is in between 0 and 1. Okay, notice this is not less than or equal to. Okay, these are just less than signs, right? Okay, so b is 0 is less than b is less than 1. And my range stays the same, actually. Okay, so f of x is still going to be greater than 0. So what does that look like graphically? Well, it kind of changes. So now as I move across my domain, again from left to right, we can see that my output is declining, right? It's going down. It is decaying, as we say. All right, so this is why we call this exponential decay versus this one when we're growing is exponential growth. Okay, So those are two main types. And notice here, again, without any transformations, my y-intercept is at this point 0, 1. Okay, for both of these, it's at 0, 1. Okay, so something important to notice, especially as we look at transformations in the future. Okay, but for both exponential growth and decay, my y-intercept is at the point 0, 1. Okay. Okay, so I've mentioned transformations a couple times, so let's take a look at these here. We've got a general form for transformations that we've kind of seen before, all right? We've got f of x is equal to a b raised to the x minus h plus k. Okay, so we've seen this like when we looked at square root functions, we had f of x was equal to a square root of x minus h plus k. Okay, now these are the same sort of values doing the same things that they're doing for our exponentials, right? Now be careful, okay, some students get messed up and say, and they think if I have 3x squared, okay, they think that that's equal to 9x squared because they're taking this exponent and raising 3 to the second power as well. Okay, but these guys are not equal to each other. Okay, so just be careful when you have some a value here that you're not also raising that a value to your exponent, all right? All right, so let's take a look at what each of these look like or what each of these does for our transformations. Okay, if I have h and h value in there, h is our horizontal translations, okay? And our translations are just shifting, okay? They are shifting left or right for our horizontal translations. Okay, so that's all this means, is left or right shifting of my graph. Okay, so if h is positive, okay, then we're going to move h units to the right. Okay, and this is always a little counterintuitive because if h is positive, then in this general form, you're going to see x minus h. Okay, x minus h. So that's when we're moving to the right, okay, to the right h units. And if h is negative, then we're going to move to the left h units. Again, if h is negative, what your general form will look like would be whatever your base is raised to the x plus h, right? So if it's negative minus a negative, then that's going to look like x plus h. Okay, so that's when we're going to move to the left, all right? Okay, now taking a look at what our k does. K is our vertical translations. Again, that is just a shift, but now we're going to be shifting vertically, so we're going to shift up or down. That's all my vertical translation means. Okay, so if k is positive, then we're going to move up k units. Okay, and if it's negative, then we're going to shift down k units. So whatever k is, if it's 2, I'm going to take my graph, shift it up 2. Okay, if it's minus 2, I'll take my graph, shift it down 2. Okay. And then our last one, our a value here, is determining our reflections and dilations. Okay, reflections, if a is less than 0, so if it's a negative value, then that is an x-axis reflection, which we'll see what that looks like in a bit. And if the absolute value of a is greater than 0, then we know that that is going to be a vertical stretch, or a vertical compression, or compressed vertically if you have, say, 0.5 or some sort of fraction that's in between 0 and 1, okay? So if a is in between 0 and 1, then we have a vertical compression, and if a is greater than 1, we have a vertical stretch, okay? So let's take a look at what those look like on our graph. Okay, so I pulled up Desmos here. Again, I've got f of x is equal to a b raised to the x minus h plus k. Okay, so this is just our general form for transformations. Okay, so let's take a look at what each one of these does as I move these sliders, all right? So my base right now is just 2. Okay, I've got a base of 2. And then let's see, h right now is 0, but what happens when I move h into the positives, okay? You can see now that we are shifting this whole thing. We're not changing the shape of it, but we're just shifting it over to the right, okay? And if I move h into the negatives, now I'm shifting it over to the left by however many units h is, okay? So that's how h transforms my parent function. Bring that back to 0. Okay, and then k, again, if k is positive, it's not changing the shape at all. It is just shifting it up or down if it's negative, however many units k is. Okay, so hopefully you can see that going on. And then I'll go ahead and skip b right now, but let's move on to a. if A is, we know that that is our dilations and reflections, right? Okay, so if A right now is 1, okay, but if I move that to be greater than 1, okay, it kind of looks like it's shifting it to the left, but what it's really doing is it's vertically stretching our graph, okay? It's a vertical stretch when A goes further and further from 1, okay? And then if A is in between 0 and 1, you have this bit of vertical compression, okay? And then once A becomes negative, okay, now we can see that flip on our x-axis, right? We see that flip on our x-axis, that reflection, okay, and it's doing the same thing. It's vertically stretching or compressing, okay, but now it's going to be flipped about our x-axis if it's negative, okay, so something to keep in mind there. Okay, now let's take a look at what happens if I change B, okay? B, when I change my base, okay, something kind of interesting happens. It almost makes this a sharper corner, rather, okay? If it is a larger number, okay, if B is a larger number, then I have this sharper corner here, okay, and then if it gets closer and closer to 0, sorry, closer and closer to 1, when B is 1, well, then I just have 1 raised to some power, which is always going to be 1, right? So that's when I just have this horizontal line here. Now notice the point here, okay, I've got this point 0, 1, and as I shift B, that point is always, that's kind of like what we're rotating this about, right? Or what we're transforming this about. That point stays the same no matter what B is, okay? Now, that's different with A, right? When I stretch A or compress A, okay, that does change my y-intercept, okay? But, bring that to 0, okay, but when I move B or when I change my base, that y-intercept actually stays the same. Okay, so something important to kind of realize there. Okay, and then when B is in between 0 and 1, that's when we see this new shape, which looks like exponential decay. All right, so we've got exponential decay when B is in between 0 and 1, and then when we are above 1, now I have exponential growth again. Okay? Okay, so that's kind of the concept that we're looking at today. So let's go ahead and look at a few examples. Again, we're just going to be graphing these exponential functions. Okay, so our first one we're going to graph is y is equal to 4 raised to the x power, and then we need to state the domain and the range. Okay, so we can do this by creating a table. All right, one way to graph any function is just by creating a table. Okay, so I'm going to go ahead and pick some x values and plug them in and see what my output is. All right. So if I pick, let's say, -5, okay, for x, now I have 4 raised to the -5th power, which is the same as 1 over 4 to the 5th power, right? Okay, so that's going to be 1 over 100. So 1 over 100 would be my output at -5, which is going to be really, really, really close to 0, okay? Really close to 0, but not quite there, right? Okay, and then if I have -1, okay, that's going to be 4 raised to the -1 power, which is just 1 over 4. So at -1, I've got 1/4. Okay, and then let's see if I've got 0. Well, again, I'm always going to have a y-intercept at 0, 1. Okay, so my output is going to be 1. And then if I've got 1, now my point moves up to 4. My output moves up to 4. Okay, and then 2 moves me all the way up to 16. Okay, so we've got a point there, right? So if I were to go ahead and connect all of those, I'm going to go ahead and just put up another graph here. It's going to look a little bit better than mine, but this is what my graph would look like, okay? So we could just connect those dots that we created, okay, and that's what my curve would look like for exponential growth, okay? And my let's say my base is greater than 1, so I know that it's going to be exponential growth, right? Okay, now our domain and range. Now again, my domain is going to be all real numbers for my exponential functions. And notice that my range, again, it looks like it's touching the x-axis, but it's actually not, okay? It's approaching y is equal to 0, but it's never actually getting there. So my range is going to be y is greater than 0. My domain is all real numbers, okay? Okay, let's check out example number 2. Okay, now we're graphing what's going to hopefully look like exponential decay because my b is this fraction here that's in between 0 and 1. And we have some other transformations as well. But again, we need to state our domain and our range by the end of this, all right? Okay, so we're going to do the same thing. We're just going to build a table here and pick some x values. Now I'm going to pick some different x values than I did before because I've got this horizontal translation, right? So I'm going to move, I know I'm moving to the right 4 units. Okay, so I probably shouldn't pick like 0 for x, right off the bat. So instead, I'm actually just going to pick 3, okay? So I'm going to pick 3 and put 3 in for my x, and I'm going to get negative 11 over 2. If I pick 4 and input that in, I get negative 1. If I pick 5 and input that in, I get 4 over 5. 6, input that in, I get 1.52. That's approximately 1.52. And when I input 7, I get approximately 1.81. Okay, so I can go ahead and plot out all those points, and my graph is going to look something like this. Okay, something like that. Okay, now it's important to note, if I were to go ahead and kind of stretch out the window of this and plug in some numbers bigger than 7, okay, my graph is going to look something like this. Okay, so I should be able to see here, if I'm asked to state the domain and range, that's when I should be able to see what am I approaching, or what does it kind of look like it's touching, but I know that it's not. And that value is going to be y is equal to 2. Okay, so my domain again is going to be all real numbers. Now it looks like there's a vertical asymptote here, right, at 2. Okay, but it's important to understand that for my exponential functions, I don't have a vertical asymptote there. Okay, I can input any value for x. There's no restrictions on what I can put in here for x. Okay, it can be anything. So there's no vertical asymptotes for me here. It just kind of looks like that when I have a smaller window like this. Okay, so my domain is all real numbers, and my range, what is my output going to be? Well, y is always going to be less than 2, and it's going to approach 2 as it goes off into infinity. Again, that's looking at end behavior there. As my horizontal asymptote is going to be 2. Y is equal to 2 at that point. Okay, let's take a look at our last example. This one is a vehicle that we're looking at purchasing. Okay, it's valued at 30,000, and it's depreciating at a value each year by a factor of 15%. Okay, so when it's depreciating, that means it's going down in value. Down in value, right? Depreciating. Okay, so that means we should be working with exponential decay, right? So hopefully when we graph this, it looks like an exponential decay function, and we'll know we're kind of on the right path. Okay, we're asked to draw a graph of the vehicle's value for the first 20 years after the initial purchase, and then see how much it would be worth after 3 years, and then the vehicle's worth after 15 years. Okay. Now for this, we're actually going to use a special type of exponential decay. When we have a constant percent of decrease, we can use this formula here, okay, where I have a is equal to a parentheses 1 minus r raised to the t power. Okay, 1 minus r, that's what we call our decay factor. Okay, that's how much our value is decreasing each year. Okay, and a is going to be our initial purchase value, and t is going to be our specific time period. Okay, so my independent variable here is t is time. So as time changes, the overall value, the output here is capital A of t. That is going to be the new value of my car. Okay, so that's what we can use for a situation like this. Okay, so I've got my calculator out now. We're going to go ahead and graph this. Okay, so I'm going to go ahead and go y equals. Okay, our initial value was 30,000. That's what we're going to purchase this thing for. We're going to decrease by, I'll put a 0 in there, 15%, so 0.15. Okay, that's my r. Okay, and raise that to our power of our variable. Okay. Okay, so this is what our equation should look like going into our calculator. Now I'm just going to show you my window here just for some context. So it doesn't make sense to have negative time, right? So when I purchase it, that's what's going to start my exponential decay. So I'm going to have a minimum x value of 0. We're asked to graph out for 20 years. Okay, so my max x value is going to be 20, and we'll just go 1 year at a time. And it also doesn't really make sense to have a negative car value, at least in the context of this problem in real life. It certainly does. But and then our max value, I just put something over 30,000. So I put 35,000 with a scale of 2,500. Okay. So that's kind of the window that I'm looking at to give me a better view of what this might look like. So I can go ahead and hit graph. And I'm going to get something that looks like this. Okay, now this does look like exponential decay, which is great. This is what we were hoping for. Okay, and now we're asked to find the vehicle's worth at 3 years and then 15 years. Okay, so let's go ahead and hit second calc, and we'll just hit 1 for value. And x is going to be 3, okay, because that's at 3 years. And if I hit enter, I'm going to get a value of $18,400 and about $24 for my vehicle after the first 3 years of owning it. Okay, so it's going to drop by almost half, okay, in value. It's going from 30,000 to just over 18,000. So we're losing a lot of value on our car just in that first 3 years. Okay, and then we're asked to find the car's value after 15 years. Let's go ahead and do the same thing. We'll hit second calc, 1 for value, and we'll hit x is equal to 15, hit enter, and it'll give me the value here of $2,600 and about $21. Okay, so at 15 years, this is how much that new vehicle would be worth for us. So not a whole lot after 15 years. Okay, so again, here is our graph that we looked at, and then after 3 years, again, we're looking at a vehicle that's worth $18,424, and after 15 years, we have a vehicle that's worth just over $2,500. Okay, so it depreciates quite a bit over that first 15 years. Okay, so if you're looking to, say, buy a vehicle and you don't have $30,000 to buy a brand new one, okay, 3 years old for a vehicle is still pretty new, right? So you can buy a pretty darn good vehicle for almost half the price of what the new one would cost if you just look for one that's a couple years old, 3 years old, and you should be able to find a vehicle in your price range, okay? So that is an example of using our exponential decay or our exponential functions in real world. Awesome. So there you go, guys. Good luck with your practice.